All right, so our topic for this week three-way tables and k-way tables. So most of the conceptual work that we have to do in thinking about k-way tables happens already when we go from two-way to three-way tables. So we have to come up with a bunch of new ideas and concepts for thinking about how we can miss being independent or what kind of dependent structures we have. For the case of three-way tables that we'll begin talking about today and spend this week on, these concepts sort of all have names. But as we move into k-way tables, quickly there become too many concepts to have names, so we have instead notation for them. So the idea is that we're going to get new models of association, better than not independence, but sort of nuanced versions of not independence. You know, like different ways things can be correlated or related. And we're going to need goodness of fit tests for each of these concepts. So for example, we're going to get something called the Cochran-Mantel-Hansel statistic. This is a test for a particular one of these types of structures called conditional independence, which is particularly important. This is a test for goodness of fit of a particular model. The other thing that we can revisit now is Simpson's paradox. So I mentioned Simpson's paradox early on. And now we're going to have the tools to be more precise about what's going on and to bring it into somewhat sharper focus. So I should warn you that when you're thinking about multi-way tables, the mathematics in this situation as opposed to the matrix situation can get very complex very quickly. Mathematicians like myself spend a lot of time thinking about that math and geometry. I'll occasionally talk about some of the math that's going on, which you don't, the deeper math, which you sort of don't need to worry about. But what you do need to do is to make sure you get kind of a conceptual understanding of what can happen when we go to this setting and how it's different from the case where we only have two factors or two discrete variables. Okay, so suppose we have, now we'll have, say, three-way, so an I by j by k table. This for different k, so maybe this k could be like, I don't know, a little m or something. The simplest such table is one which is just 2 by 2 by 2. And so this is just a table of counts. Here's an example. And 1, 1, 1, and 1, 1, 2, and 1, 2, 1, and 1, 2, 2, and 2, 1, 1, and 2, 1, 2, and 2, 2, 1, and 2, 2, 2. So it has 8 entries. And those are the entries. And we can think about this as broken up into 2 by 2 tables in various ways. This is breaks it up into the first index I is equal to 1 or is equal to 2, for example. But I could have chosen any of the indices and broke it up that way. But it made just as much sense to say like j equals 1, j equals 2, and then I would have n 1, 1, 1, so now j is not changing, n 1, 1, 2, that happens to be the same, n 1, and 2, 1, 1, and n 2, 1, 2. So it's the thing in the middle here that's not changing. And over here I would have n 1, 2, 1, and 1, 2, 2, and 2, 2, 1, and then 2, 2, 2. All right, so this is the same table, 2 by 2 by 2 by 2 table presented in two different ways. And the other way that you'll typically see these presented is not as a bunch of tables, but as one big matrix, which these sort of implicitly are. That is, I might separate, so for example, there's an example in the notes called a death penalty example, and it has to do with whether the defendant and the victim were white or black, and whether they received the death penalty or not. And this is the death penalty, yes or no, defendant race and victim race. And from this I can get a table, 19, 132, 0, 9, 11, 52, 6, 97. So I can think about this as two 2x2 tables or as one 4x2 table. And such a thing is called a flattening of the table, because we took this cubic thing and we flattened it down to a two-dimensional thing. But just like what we talked about 2x2 tables or I by j tables, when we turn an I by j table into a single vector, flatten it out, we lose some of the information, right? So we sort of forget about which variable is which. And if you just flatten this out and forgot where this came from, you would lose the information of the 2x2x2 structure. So making a flattening kind of is just a piece of notation, but it also often reflects a hypothesis. So here, usually the flattening you'll see is the one where you want to think about this as being the thing you're predicting, or the dependent variable, and this as the predictors, or the independent variable. So that's the case here where we're trying to predict that. So there's some meaning, but it's not the whole story of the table. So there's some little pictures that I like to draw to keep track of this, which I'll occasionally use, and which are, for the purposes of this class, just something that's a convenience, although they're certainly a more formal object. So one way you could think about this is that a two-way table is like I have two factors coming out of some true table. So you think about this as n, and it has two factors like a and b. And I have kind of two ways of flattening that table. It's already flat, which is that I can think of it as going from a to b, or I can think of it as going from b to a. And I could bend these other various ways. This is like taking the transpose of the matrix. Okay? And in the case of a three-way table, I have just more choices of flattening. So I have three factors, like defendant, victim, and penalty. And I could choose to put the defendant on one side and the victim and the penalty on the other side, or I could choose to put, as we did here, the penalty on one side and defendant and victim on the other side. So each of these sort of possible ways of pulling these wires apart gives me a different flattening of the table. So we have only kind of one choice in the 2x2 table. As we have more ways to our table, we get more choices as to how we can flatten it, and they have different meanings. So there's marginals. In a 2x2 table or a two-way table, we have one-way marginals, right? There are one-way marginals. That is, right, these are just called the row and column sums. So in a multi-way table, in a three-way table, we still have one-way marginals. So say we have variables, x, y, and z in a table. We have marginals that look like this, probability that x equals, 0, probability that x equals 1, say. Right? And we have the marginal, so that's the one-dimensional or one-way marginal for x. And we have the same thing for y. And we have the same thing for z. And these are vectors, and they're just the same kind of object as in the two-way version. But now we also have bigger marginals, which is that we can, instead of summing over all but one vector, we can sum over just one of the variables, right? So we can get tables we can get a table like probability that xy is equal to 0, 0, probability that xy is equal to 0, 1, probability that xy is equal to 1, 0, and probability that xy is equal to 1, 1. So this is another marginal, but this is a two-way table, which is a marginal of the joint distribution on all three variables. Right, so as I have more ways, all of the previous ways, all of the lower order things becomes the kinds of marginals and the kinds of conditionals that we can obtain.
I'm so sorry, I can't
Yeah. This is a two-way table, which is a marginal of the joint distribution on x, y, and z. Sorry. So in these little pictures, if I have a table here, I could think about the marginal as like I ignore one of the variables, I add over it. Right? And I have two choices in a two-way table. And in a three-way table, I can I could be left with a 2-by-2 table by summing out one of them, or I can sum out two and be left with a one-way table. So that's a two-way marginal. This is a one-way marginal. So these these marginal tables, if my overall table was n, or nijk were the entries, right? My one-way tables would be like n plus k would be a one-way table as k varies. And I plus k would be a two-way table where I'm summing over whatever the middle one was, and I'm allowing I and k to vary. Which is a marginal. This is a two-way marginal. And of course, well, this is not at all a marginal, that's just the table. But it's kind of a zero-way marginal. Or I could sum them all, and that's, like it's not a zero-way marginal, it's a three-way marginal. If I sum them all, that would be a zero-way marginal. And I can also get conditionals. So in a two-way table, the conditionals are just the rows and the columns, right? So if I have a table like this, n11, n12, n21, n22. So this is x equals 1, x equals 2, y equals 1 or 2. The x equals 1 conditional is just this. The x equals 2 conditional is that, right? Similarly, we can have, so I could write that as like n1j. Right? This says 1 I'm fixing. And I'm allowing j to vary. So I can think about this as like a vector, like n1, 1, n1, 2, or n1, 1, n1, 2, n1, 3, if I had three factors for j, or three possible outcomes for j. Similarly, I can get conditional multi-way tables. If I start out with my nijk, I can think of n1, 2k as a conditional one-way table. ni1k as a conditional two-way table. Right, this is analogous. This is the marginal where I sum over the middle variable, and this is one where I fix the middle variable. So in a marginal, I sum over it. In a conditional, I fix it. Okay. And so up to that logic, a lot of the way that we think about like the maximum likelihood estimators and so on for simple models are just the obvious versions of that. Right? So if I want to estimate the conditional, I just divide this by the relevant total. Right? So like p hat 1, 2, k is n 1, 2, k divided by n 1, 2 plus. P hat I 1, k is n I 1, k over n plus 1 plus. Sorry, this is conditionals, so I want to say the other way around. This is probability of k given I equals 1, j equals 2. And this is probability of I, k given j equals 1. The marginals, similarly. The marginals are ones where I just have to divide by this. Right? So this is like p plus plus k is n plus plus k p hat divided by n plus plus plus. So as I hope that suggests, the conditional and the marginal tables are different objects. So think about in a 2 by 2 by 2 by 2, conditional and marginal are not the same thing. So I can construct a conditional 2 by 2 table like this, or I could construct a marginal 2 by 2 table like that. And of course, they're just different numbers. And because they're different numbers, they have different odds ratios, right? You have different measures of association. In fact, we could have that, say, the log odds of, let's call it AB, and I could compare that to the log odds of AB given C. So this is AB summing over C and AB given C. This is the conditional, this is the marginal. Right, it could be that one of these is positive and one of them is negative. So they don't even have to go in the same direction, right? So this is another way of addressing this idea of Simpson's paradox, that the relationship between two variables can reverse when you include a conditioning variable, right? Like my example with the dogs, right? Once we know what the species of the dogs is, it looks, if we ignore the species, it looks like it's better. They're bigger when they're in the city. They're healthier in the city, or in the country rather. Once we take into account the species, the relationship reverses. So that's something that can happen. And the fact that this can happen is called Simpson's paradox. So just to sort of recap, we have a joint distribution. We have marginal distributions. Well, I'm going to actually move this, sorry. We have joints, we have marginals, and we have conditionals. Thinking probabilistically, we have a joint distribution, a marginal distribution, and a conditional distribution. We have joint counts, which is just the table we started with. We have marginal counts, where I sum over one of the variables. And we have conditional counts, where I hold one of the variables fixed. And we have estimators for each of these, where I divide by the appropriate thing. right? These are the estimators given the counts of the distribution. The estimators given the marginal counts of the distribution. I hope by now it's clear how you would construct something like that, right? This is this type of estimator. And similarly, we have different notions of product multinomial sampling. So as I vary what I'm fixing, what becomes the sample is different, right? So whereas in the two-way table, I have this choice of, well, I fix the rows, or I fix the columns, or I fix everything. And I get different, right? I fix everything. If I fix just the total count, I get multinomial sampling. If I fix just the rows, I get product multinomial. If I fix just the columns, I get a different product multinomial, right? So here now I have more choices. Right? Instead of saying I fix the rows, I could say I fix one of these subtables. I could fix a marginal table, or I could fix a conditional table. So I have more choices on what I can fix, and I get, therefore, more notions of sampling. So let's see how an example of how that works out for, say, odds ratio estimation. So, right, we could consider marginal and conditional odds ratios, like in this Simpson's paradox example. And there's nothing special about this. I mean, these are just, we get a 2x2 table in the appropriate way by conditioning or by summing over the variable we don't care about. And then we construct the odds ratio from that table. So for example, if I want a marginal one, let's call it A plus C, that's just N1 plus 1, N2 plus 2 over N1 plus 2, and 2 plus 1. It's a marginal odds ratio. And if I wanted a conditional, I would say something like AC given little b, where I'm saying I'm picking a particular state, of little b, of the b variable, little b, which is the particular outcome. I'm not saying what it is in particular. There's many of these. Okay, so if the marginal odds ratios are 1, we would say that the table is marginally independent. This table, if the conditional odds ratios are 1, we'd say that we've seen conditional independence in this table. Conditional independence is this idea that we've kind of explained away something. We've explained away one factor in terms of another. Okay, so now let's look at some of the specific models that we can consider for a three-way table. Explore different ways of writing these. There's many different equivalent representations to distinguish between these models. I'll start with this one in terms of these sort of little pictures. Models of association. So in the two-way table, we basically have two choices. We can have an arbitrary table of counts, or we can claim that this table is actually equal to two little tables, one for the row and one for the column, and we take their outer product as vectors. So this would be saturated, and this would be independent. To claim that this bigger thing is actually explained by this smaller thing, and the independent model sits inside of that. And there's some other models that you might consider, like fixed rank tables and things like that, but we didn't talk about that. So then for a three-way table, there's just more choices, right? So I can have the saturated model, where I'm allowed to do arbitrary I have any probability distribution. I have the full degrees of freedom. I can have independence, full independence, where each of the random variables is independent of each other. But I can also have things like, well, two of the random variables are saturated with respect to each other and are independent of the third. This is called joint independence sometimes. And there's three different ways I could do that. You can see the table gets bigger. There's many more possible ways of grouping them together. And I can have this other thing called a conditional independence. Which says that there is a relationship between these variables, but that relationship is mediated by some specific factors. And we'll explain more about what this means. So in a sense, it says, OK, these things are independent, but the measures of effect are the odds ratios or the parameters, factors into parameters that only consider the first two and only consider the second two. And the first and the third in this picture are independent given the thing in the middle. OK, so in your text and in your book, there's some time now spent on the names of these three-way tables. In some sense, this is a necessary thing in getting a grip on it, but it's also in some sense like charming impossibility, because for three tables, just like when there's only 3 points in a graph, it's not too hard to list all the possible graphs. But when there's 100 points in a graph, it's going to take you a very long time to list all the different possible graphs, and you're not going to try to give them all a name. So this project of breaking up the dependence structure and giving each dependent structure a name is like naming the graphs on some number of nodes. When we only have 3 nodes, it's possible. But when we have some large number, a many-way table, it's impossible. So, but it's good because it helps us get some intuition about the departure from independence represented by each of these types of models. But we really are going to have a combinatorial explosion when we get to k-way tables, and we have to give up the idea that we could ever give them all a name. OK, so this first model, independence, or mutual independence, or just plain independence, I'm going to give you just a bunch of different ways of thinking about it to start out with. Okay, this is an easy one, but it'll get us oriented. So this is ABC. I have discrete categorical variables. There's various notations. So one of them is called graphical model notation, which is what you'll see a lot of in this class. It's in the online notes, and it shows up in Agresti, and is a great further thing that you can do a lot more study on. In this graphical model notation, each variable gets a node in the graph, and we connect them if there's a certain type of relationship, which I'll tell you about in a little bit. But here's the graphical model for independence. It's just the graph on 3 nodes, and there's no edges whatsoever. There's this, what you could call tensor notation that I've been using over here, which is what they would use, say, in physics. They were talking about something like this. And that's this picture, A, B, and C. Here I might label the wires instead of the graph. There's a simplicial, what we would call in math a simplicial complex, or what you'll see in Agresti, something called log linear model notation. And in this notation, what we emphasize are not the variables, but which variables have been grouped together and allowed to depend on each other. And for an independence model, this notation is just ABC. So we're interested in the subsets A, B, and C, and no other subsets. Okay? We'll see in a minute that we could get more interesting subsets. Like if I put an edge between A and B, I would include the subset AB as one of these pieces that's allowed to have a dependence. We can talk about the independence statements that are satisfied by the model. In this one, I could say, well, everything is independent of everything else. A is independent of B given C, or I might break that up into saying A is independent of B, A is independent of C, and B is independent of C. So all the possible independent statements that could hold. And if you think back to the definition of independence that you might have learned in an elementary probability class, remember that it's often defined in terms of parameterization or factorization. That is, we say that, for any, so suppose A takes values little a. So little a is an outcome of big A. This is yes or no, or red, green, blue. This is the variable, random variable, which could take values red, green, or blue. B, little b, c, little c. Then in an independence model, we're saying that the probability of the outcome ABC, red, small, 1299, is equal to the probability of A, probability of B, probability of C. Right? It's a factorization property. And what we're saying here is probability that A equals little a, B equals little b, C equals little c is equal to the probability A equals A times the probability B equals B times the probability C equals C. Right? That's what we're saying. It's just notation for this expression. And when we go to write down our model or parameterize it, we might also express this by saying the probability of ABC is proportional to some parameter which depends only on the state of A times some parameter that depends only on the state of B times some parameter that depends only on the state of C. Right? For example, we might say something like this is theta A, theta B, theta C times 1 over the sum over all possible A, B, and C, theta A, theta B, theta C. So this is a perfectly good way to describe the independence model on 3 variables. And as the course goes on, we'll tend toward descriptions that look more like this. When we get so that we're ready for log linear models. And the last description that I would give you of independence is one that's in terms of effect size. So an independent structure on variables A, B, and C is one. They're independent if all effect measures are no effect, right? What I mean by that, well, we could say, well, we want that probability of ABC, probability of A prime, B prime, C equals the probability of A prime, B, C, probability of A, B prime, C. So this is telling me that, and this has to hold for all C and for all A prime, B, B prime. So this says, conditioned on C, A and B are conditionally independent. And I can say the same thing for the other guys, like A, B, C, A prime, B, C prime equals P, A prime, B, C, P, A, B, C prime, and so on. Or I could say something like all the odds ratios are 1, or all the relative risks are 0. That I could construct from the table. There's no relationship. There's no effect. So one thing to be careful about is, remember, now we have different notions of independence. So we have mutual independence, we have marginal independence, we have conditional independence. And it is true that mutual independence implies marginal independence. But the converse is not necessarily true. In 2 by 2 by 2 tables it's true, but in general tables it's not. One way to say this in pictures is something like, if I can write a table as an independence model, well, then it's also true that if I sum over one of these things, that's equal to a picture like that. I've summed over the last one. And when I sum over a single vector, I just get a scalar. So this says this thing, ignoring this piece. This is some bigger guy. It has two factors. It has two factors. It's independence. That's a way of saying that mutual independence implies marginal independence, i.e. if the Threeway table is independent, so are its marginals. If I have some big table, 1, 1, 1, 1, 1, 2, 1, 2, 1, 2, 1, 2, 2, P2, 1, 1, P2, 1, 2, P2, 2, 1, P2, 2, 2, and I tell you that it's independent, then its marginals will also be independent, its conditionals will also be independent. P plus 1, 1, P plus 1, 2, P plus 2, 1, P plus 2, 2 is also independent, and so on. Other possible marginal tables that I could make. So just by the way of checking, let me just do a quick check of something. If I write a table like this, and I say that this table is multinomial, so a statement like n plus plus p11, and you can imagine me adding in marginal or pluses or conditional things in this statement if we want to make it. Right, I could add a plus, here plus 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 plus, or I could add some k value, some value for c. So suppose I have a table, right, that's multinomial according to that distribution, and this table is independent. Let's call this p. So this joint distribution is independent or marginal or conditional distribution. What do I expect about this? Is it 1? So this is a random variable, right? No, it's not 1. But I just expect that it's what its expectation is 1, and the log of this thing has some appropriate normal distribution, right, in terms of the 0, 1 over, and 1, 1, and 2, 2, right? Just to remind you where we are. Okay, so when we say something like this. This independence holds at the theoretical level for the true population, but of course when we pull any particular table, this odds ratio will never actually be, or very rarely actually be 1. Right? It's just something we expect to be 1 on average. And we understand something about the distribution of it so that we can do tests. So nothing about that statement, as I said, changes when I add, say, a letter here, like C, 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 C. So now I just told you how to test for conditional independence, right? It's just another table. So the philosophy for doing hypothesis tests for constructing maximum likelihood estimates is analogous to the 2x2. This is for the independence model. So as my model gets more complicated, some of these MLEs will no longer be something where you can take a simple formula, like taking the product of the marginals. Sometimes these MLEs will become something you have to solve with a computer. That's what this asterisk is for. But conceptually, it's analogous, right? So like my p hat ijk under the independence model is just p hat I plus plus p hat plus j plus p hat plus plus k. So I just take my, where p hat I plus plus is n I plus plus divided by n plus plus plus. So we're just, in the case of, at least in the case of these independence and joint independence models that we'll talk about in a second, all we do is the obvious thing, the 2x2 thing, extension of the 2x2 thing, carefully, because it's easy to lose track of what we're summing and what we're fixing. But conceptually, it's really the same idea. And our tests for independence, as this expression suggests, are tests using Pearson or deviance are the same, except just that I have to calculate my EIJ differently. Right, our null hypothesis is independent. Our alternative hypothesis is not independent, or more accurately, saturated. And then I want to compute the expected values. How do I compute the expected values? I compute the maximum likelihood estimate of the probabilities, which is this sort of outer product, the product of the marginals. And then I multiply by the total, and then I get the expected cell counts. 8 expected cell counts now. And then I just subtract the observed and divide, or take the log and get a chi-squared statistic. So it's just we just reduce it to the multinomial case. There's one variable multinomial case with a particular method for getting these. And so I want to note something here, which is, as you remember from your homework where you had to draw this picture of the simplex and the surface, the independent surface in the 2x2 case sitting inside the simplex, really this thing is a subset of this, right? These models are contained in these models, the saturated models, which is the full simplex. That continues to be true, right? So really, we've thought about this as being the only alternative, but really what we're doing here is a nested test. We have one model, and it sits inside another model, and we're comparing them. We're trying to see how much better does this thing fit than that, right? And in this case, because this fits everything perfectly, that's fairly simple. But you can imagine doing this for more general inclusions. They weren't really an issue for 2x2 tables, but for 2x2x2 tables and above, there's more complex inclusions that can happen. If you think about this graph notation, which I have not fully explained yet, but which we'll get to, I could think about, I have A, B, C, and I have a model on these three. I might have a model like A and B are somehow related, but they're independent of C. Or I might have another model like A and C are related, but they're independent of B. And then I could have another model entirely up here, which says, well, A and B are related, and A and C are related, but not B and C. Or the dependence between B and C goes through A. Okay, so now I have more than one inclusion. This model is included in that, and I can do a chi-squared test. This model is included in that. This model is included in that one. This model is included in that one. And this one is, by the way, included in the sort of, saturated model where I allow them all to interact however I like. Okay? So the chi-squared test purely for independent versus not independent is kind of short-circuiting this and comparing this model with the fully saturated model. But now that there's more ways to go wrong, structured ways to go wrong, or ways to fail independence, really there are all of these other tests lurking in here. The nice ones are the ones that are purely nested, where I can say, well, I can compare this with this, and I can compare this with this using the same hypothesis test logic. But there's also, unfortunately, some that are not directly comparable like that. And we have to think about some other way of deciding, if I have to choose between this model and this model, which one should I pick? For example, we could just do these tests and see which one gets a better fit. Okay, but for example, you can imagine a complex model and a simple model. The simple model is not embedded in the complex model. The complex model fits better. Eventually, we're going to have to figure out some way of penalizing the complex model. That'll be sort of one of the last topics we get to. Okay, anyway, so that's sort of an aside for now. It'll warn you about some of the complexities that are ahead of us. But for this one layer test, where we're just comparing independence with saturated, all we need to do is estimate the MLE in this way by taking the outer product of the marginals, multiply Pijk hat, this Pijk hat, this is Pijk hat equals Pi hat Pj plus plus hat Pk plus plus hat. Multiply this by the grand total to get expected counts for every cell under the independence model, and then compute Pearson or deviance sum. Now we're summing over 3 indices, ijk and ijk minus the expected, so the observed minus the expected, ijk squared divided by the expected, or twice the sum over ijk for the deviance test, observed log ratio of observed to expected. And we can compute the degrees of freedom in the usual way. Number of degrees of freedom of the saturated model minus the number of degrees of freedom of the independence model. As that suggests, when we're doing these other comparisons, we're just going to be making different subtractions. This one, degrees of freedom this minus this, degrees of freedom here minus that, and so on to test each of these inclusions separately. So in this case, that degrees of freedom is ijk minus 1 minus I minus 1 plus j minus 1 plus k minus 1. So one thing to notice here is that as we consider multi-way tables, right, as the number of ways grows, so if I had like a 2 by 2 by 2 table, and there were a little k of such things, this number is going to become 2 to the k minus 1, which grows very fast. This number is going to become k. Right? And then we can think about things like marginals. So suppose I took marginal odds ratios, 2 by 2 tables. How many of those are there? Well, I take my k ways, and I choose 2 of the ways to keep, and I sum over the rest. So as k choose 2 of those, k minus 1 divided by 2. So for very small k, it's feasible that the marginal odds ratios could describe what's going on. But for k getting larger, of course, this is much bigger than this number. It's much bigger than that number. So don't get confused by the fact that this is sort of important enough, or enough information in very small cases. That's fine, but keep in mind that that's just a coincidence of small numbers. So let's start on one of these examples that's from the notes, which is this Boy Scout example. And this, we're not going to get through all of it today, but it will start to show sort of the value of thinking about these different models and how we consider different versions. Boy Scout and delinquency. Boy Scouts. So here we have n plus 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 equals 800, and we have a 3 by 2 by 2 table. And the table is socioeconomic status. That's the 3-factor by Boy Scout. Yes or no. By, this is high, medium, low. And by delinquent. Yes or no. Okay, so as usual, this table, we're thinking of some factor here, delinquency, as being the thing we're interested in predicting based on the other 2 factors. And so we present it, we have some table n, and we present it by choosing a flattening. Boy Scout delinquency, as we say, well, we want to think about it as going from sort of like a linear transformation or a transformation of some kind that connects scouting and socioeconomic status and Boy Scout and predicts delinquency. So we're going to present it that way. So SCS as the first factor, sort of lexicographically, second factor Boy Scout. So low, medium, high. Boy Scout is the second factor, lexicographically. Yes or no. Yes or no. Yes or no. And then our predicted thing is going to be delinquent. Yes or no. And the numbers, let's put them in, 11, 43, 42, 169, 14, 104, 20, 132, 8, 196, 2, and 59. Of course, the table is in your notes. So the first thing we could do is perform this skipping test that goes right from independence all the way up to saturated and doesn't attempt any of the intermediate models. So if we do want to do a test for independence, we compute our maximum likelihood estimate by taking the marginals. So the SES marginals, the Boy Scout marginal, delinquency marginals, compute their maximum likelihood estimators, just the number that are that divided by the total, multiply them together to get an estimator for the probability of each cell, multiply that by n plus plus plus, 800, we get expected values, and then we can compute our chi-squared statistics. And if you do that, of course, we need to keep track of the degrees of freedom. Degrees of freedom is 3 times 2 times 2, minus 3 minus 1 plus 2 minus 1 plus 2 minus 1, which is 11 minus 4, minus 1, 2 minus 1, 11 minus 4, 7. So we get a chi-squared test with 7 degrees of freedom. And if you do that, the p-value is very small. It's very close to 0. So what does that mean? Well, it means that there's some dependence in the data. It doesn't tell us anything about where it is. Of course, we could look at residuals or something like that. But it tells us there's some signal there. And what we should then do is look at more nuanced alternative models. Not just independent versus not independent, but some of these things, some of these things in the middle that I just erased that could be other possible explanations. Right?
Do you have to plan what you want to compare beforehand, though? Like, if you just keep testing different dependence models, aren't you going to test, like, over-test this data?
That's a good question. That's a very good question. And there's a couple of answers to that. So one is that, yeah, you do have to be careful. Because of this nesting of the structures, what people often do in this type of inference is to assign kind of a penalty to complexity, right? Because, for example, the saturated model will always fit the data, right? If I use more complex models that have more parameters, I expect them to have a better fit. If I use simpler models with fewer parameters, their fit is more meaningful. And so one of the strategies, which we'll talk about probably in a couple of weeks, is that you can penalize models in various formal ways for having more parameters. So one thing you could do is you could just subtract the number of parameters from your likelihood score. Right? Your likelihood of minus number of parameters, or some function of the parameters. And that helps.
So you're using like AIC or BIC?
Exactly. Right, yeah. So we'll talk about AIC, BIC.
But does it
And other
matter
things.
that you're testing independent each time? So I'm talking more about like your probability of rejection.
Mm-hmm.
So will your alpha level change if you keep testing your data for independence? So I'm thinking like multiple comparisons.
Right. You're thinking of it as a multiple hypothesis test. So I don't think we have to worry about that here because we're not. Let me think about that for a second. Maybe we do. I mean, usually what we're going to think about it, what we're going to end up doing is saying something like, I have some models down here and I have more models here, right? And I might say, as I go to the more complex model, is my gain significant? So those are the type of significance tests that we'll do. What you're saying is that there's another kind of unspoken complexity. If we're only penalizing by that, there's this other complexity, which is the number of models that I test. The discrete parameter, kind of. So that's a valid concern. There's a few things that you can do to try to. So there are ways to have criteria like this that also apply to a number of models tested. In fact, let me think what that one's called. So there's some like machine learning flavored ones, which this is actually how they're formulated. Number of models tested, and so they're meant for the discrete case. I think this is like, I think I was going to do the VC dimension, but I'll have to look that up to remember what it is. The other kind of funny thing that happens is that, of course, in real life, we're doing all this on a computer, and there are no continuous parameters, because the things in our computer are floating point numbers, and floating point numbers have 64 bits. They're less than 2 to the 64 floating point. Right? That's a big number, but it's a finite number. So the real truth is that we are always testing finitely many models. And so we're in some sense always in this picture. It's just that there's sort of two different types of things. So it's a real problem. And if you're very good, you should do something like that and say that you're planning ahead of time what you're going to test, or you have theoretical reasons to believe that there are only certain tests that are valid and you're not going to go on a fishing expedition. I would say that the general problem of how do you correctly do that is a serious philosophical question about statistics, right? And about how we make inference from data. And so it's both a philosophical question and kind of a research question. So there's people working on, so for example, there's a talk last week, or the week before, by Adam Smith in our computer science department who works on privacy. And one of the things that they're thinking about is this kind of is like a privacy-like model that says every time you do a bunch of sequential tests against the data set, you extract some data from it, and you destroy some of your ability to make valid inference. And can you quantify the amount that's destroyed every time you ask a question? So, one strategy of saying that is you come up with an algorithm that says, the first question you ask of your data, whatever it is, uses up some of its juice, and then the next question you ask, the p-value has to get higher for significance. The next question of that, the p-value has to get higher, and it depends on the order that you ask them in. So that's something you can do. Or that seems possible, but nobody really knows the right way to do it. So it's very, overfitting, and it's a very serious problem. And it's one of the reasons, for example, that a lot of so there's this thing called the Valley of Death in medical research, right? So there's lots of research on, here's some new possible drug or some treatment or whatever, and it looks great in trials, and then when it goes to the next level of trial, either it turns out to kill the mice or whatever, or it just doesn't work, right? And one of the reasons that happens is because of this sort of multiple hypothesis testing problem, right? That we've asked too many questions of the same data, or we've tried 200 different things. All the failures were not reported, not published, and the success was published, and it was p equals 0.05, but we tried 200 different things. That doesn't really mean anything. Right? So I don't know. It's a big problem in science and statistics, and we don't have by any means solutions, but we have ideas that we'll talk about. Mostly this idea. We'll talk about this one. Okay. So let me discuss for a minute the next model to consider besides independence. This one is sometimes called joint independence. So joint independence is this model, like in graphical model notation, we say A and B are related, but they're jointly independent of C. Or in tensor notation, I would say here's A and B, and they come from the same thing, and C is unrelated to them. In the simplicial or log linear notation, we would say we're interested in the A, B, and C. So now it becomes, you were probably wondering what we're talking about when we just said A, B, C. So here's something different, right? I'm interested in the subset A, B together and C separately. The factorization property, which is directly related to this and directly related to each of these things, is probability of ABC equals probability of AB times probability of C. In terms of a parameterization, we're saying probability of ABC is proportional to some parameter that depends on the joint state of AB and another parameter that depends on the state of C. In independence statements, AB is independent of C, and also A is independent of C, and B is independent of C. And we could talk about defining equations or effects that must be zero. And that would be that any equation I can write of the form P ABC, P A prime, B prime, C prime. So now the other ones for conditional, I was holding C fixed. For marginal, I would sum over C. For this joint thing, I'm just grouping A and B and making them one variable. So all the things get a prime. Prime means some other value. And this is equal to probability of A prime, B prime, C, probability of A, B, C prime. So what we're essentially doing in this situation is we're merging A and B, which might have, say, 3 states and 2 states, into one variable with 6 states, for example, in this case. Right? So we're saying in this hypothesis would be something like, these are not independent, essentially because whether or not you're a Boy Scout is related to your socioeconomic status, right? So we're saying maybe this variable and this variable are dependent, and they're independent of this variable. that's a hypothesis about the data. And that would be reflected by this kind of joint independence model. I'm not saying it's the true hypothesis, but it's a hypothesis we can make about the data. And these are all different ways that we can express it. This is something like theta AB, C is 1 odds ratios. Let's say there's more than one of these odds ratios. S after it. Okay, so the odds ratios in that table are 1. Okay, that's a 6 by 2 table. So it has more than one odds ratio. So if we wanted to look at this equation, or this type of model for the Boy Scout data, we would do the usual procedure. Again, since this is essentially an independence model, we don't really have to do anything new. We can get an MLE, p hat ij plus, which is nij plus divided by n plus plus plus, and p plus plus k hat n plus plus k n plus plus plus. All right, those are our two parameters. They're sort of different because we're essentially have grouped I and j into be one index, a multi-index. So we only care about ij together and kk, and then our estimate, our model estimate for the joint is just ij plus times plus plus k. And then we multiply to get the expected counts, pij k hat times n plus plus plus, and from that compute Pearson and g-squared statistic. So this is just a two-way independence test on a larger table. Okay. So I'll stop now and continue next time with other models. But so what we're doing here is we're saying this is this model A, B, C. This is the test. Oops, sorry. And this is the test. Well, there's two tests to do here, really. So we have the saturated model, A, B, C. Let's fill it in. All possible things. And we have sort of two things to consider now. Is this better than independence? And does it fit compared to saturated? Right? And we'll end up adding another model up here in between these two, which is this conditional independence model, right? So that's one thing you could think about the data, which is a natural hypothesis would be, well, I don't think being a Boy Scout matters. What really matters is SES, and we think that delinquency is independent of Boy Scouting given SES, right? That would be a fairly natural hypothesis. Or the other way around. Delinquency is independent of SES given Boy Scouting, right? So those are other hypotheses that go up here. And we want to test, we can test all of these arrows or all of these inclusions with goodness of fit tests. Okay, so we'll continue in that note next time, and we'll figure out what we think, whether we think Boy Scouting does anything.